And here's the graph that this picture is about. I'm trying to be very specific here. So let's label some points. So we've got 0, 1, 2, 3, and then we go to -1, go up as high as 2. Down as low as -1. And then we're graphing y equals f of x. And the graph, that's not the right pen, that's fine. The graph looks like the following. It's a closed circle at -1. And it looks kind of like a quarter of a circle going down to this point here, but it's an open circle there. And then, well, that's really not the best I've ever done. Sorry about that. And then it's also an open circle at the origin. And it goes up to the point 1, 2, so there's an open circle there. Goes back down to the point 2, 0 with an open circle there. And over to the point 3, 0 with an open circle there. And there's also, it's defined to be 1, 1 right there. So that's 1, 2, that's 1, 1. I think that's the whole picture of the graph. And there's some questions. And this is specifically number 6. And again, this doesn't seem like the right question. Let me know, but we can certainly talk about other things about this graph as well. So first question is 6a. Does f of 1 exist? It does. Right, if you look at x equals 1, and bless you, and you look up or down, there is a point that is filled in, namely right there. So yes, f of 1 is equal to 1. I will point out that f of 0, f of 2, and f of 3 do not exist, just as to be kind of complete here. So note f of 2, f of 0, and f of 3 all do not exist. F of -1 does, though. F of -1 is equal to 0. And then the next part of this question is probably asking about the limit. Yeah. So the second part asks, does the limit as x approaches 1 of f of x exist? To answer this question, we have to look at the graph. And so remember, when we're talking about a limit, we are talking about what happens as x gets closer and closer to the value of 1. What is happening to the function y? So I will point out that as the x values get closer and closer to 1 from either side, let me zoom in here so everyone can really see this. As the x values get closer to 1 from the right, the corresponding y values on the graph seem to be getting closer and closer to +2. Same thing from the left. As x approaches 1, the y values are approaching a value of +2. So the answer here is a definite yes. And the value is 2. The limit as x approaches 1 of f of x is equal to 2. Reminder, we're not saying that f of 1 is equal to 2. It's not. We're just saying all this statement says is that as x gets close to 1, the y values get close to 2. All that says. Thirdly, and I think finally, is, sure. Okay, they really are trying to spell it out here. I thought they were just asking if it's continuous. But the third part is, so I should point out, these are the 3 questions we asked to determine if a function is continuous at a point. If the answer to any of these questions is no, it's not continuous. If the answer to all 3 questions is yes, then it is continuous at that point. So far, we've got a yes, we've got a yes. I should have written yes here. But we're about to have a no, because the third question is, does the limit as x approaches 1 of f of x equal f of 1? And the answer is obviously no. Look at parts A and B. F of 1 equals 1. And that is not the same as 2, which is equal to the limit. So then part D asks, is the function continuous at 1? And obviously the answer is no. F of x is not continuous at x equal to 1. Because although the limit existed and the function existed, they failed to be the same. Graphically, we can see that by looking at this and be like, oh yeah, well, one, it looks like it's not continuous, right? You've got the graph going here, and then you've got this hole, and you jump down there, and then you go back up there, and then you draw that part there. Definitely not continuous at 1. So hopefully, for whoever asked me about, I think it was a Maya, maybe I don't remember who it was. Hopefully, that's actually the question that they were hoping to see addressed. Let's go ahead and talk about some limits to infinity. Yeah, limits to infinity. Yeah, limits to infinity. Yeah. Sorry, one sec. Oh yeah, go to all this. Right on. Yeah. Fact. So this is kind of, so people asked about horizontal and vertical asymptotes, and this is kind of how we talk about them. Last class, we briefly talked about limits that were infinity, which correspond to having a vertical asymptote. So for example, so we'll get to the to infinity in a second. But for example, if I said my function f of x was equal to, I don't know, say, yeah, let's make it fun. Yeah, sure. Let's say 6x over 4 minus x squared. Sorry, not quite zoomed all the way up there. You might ask, where does this function have a vertical asymptote? And the easy way to answer this question is to look for where the denominator happens to be 0. To be more specific, we're actually looking where the denominator is 0 and the numerator is not 0. Because if you have a 0 over 0, we know that that kind of thing often ends up having a limit that exists that's a real value. Right, exactly. We're trying to find where the function is undefined. That is usually where we have a vertical asymptote. Specifically undefined in a 5 divided by 0 kind of way, or a 7 divided by 0 kind of way, or a 22 by some not 0 divided by 0. Because we've seen plenty of 0 over 0 types of limits, and those usually exist. Like, for example, right, we're not looking for something like the limit as x approaches 2 of x squared minus 4 over 3x minus 6. If you plug in 2 there, you get 0 over 0, and then we can solve that limit by factoring and getting the limit as x goes to 2 of x minus 2 over x plus times x plus 2 over 3 times x minus 2. X minus 2 divided by x minus 2 is 1. You plug in the 2 for the remaining x, and you get 2 plus 2 over 3, which is 4 over 3. So this 0 over 0 type, the limit is not infinity, right? The limit is some real finite number. Just like in the previous example, kind of like in the previous example, right? The limit here was a real finite number. It was 2. The graph got closer to 2 from the left and closer to 2 from the right, even though it wasn't defined to be equal to 2 when x was equal to 1. And now what I'm saying is we're not looking at that sort of situation. We don't want 0 over 0 if we're trying to get a vertical asymptote. We want specifically not 0 over 0. So what's one value of x where we might get a vertical asymptote? Sure. What's another? Right. Now, the easy way to find this is just by setting the denominator. I should really say again, by factoring and canceling if there's anything to factor and cancel. And then after you've looked for that, setting the remaining denominator equal to 0. If we plug, or if we set 4 minus x equal to 0, I would prefer to factor this as 2 minus x times 2 plus x. And then we see that we get x equal to 2 and x equal to negative 2. And those are our vertical asymptotes. Now, how do we see that from a limit kind of perspective? Well, when you're talking about a vertical asymptote, you're saying the function's essentially going up, 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 or down, 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 down. Right? When you have, like, if I was going to graph this, I don't know exactly how it looks, but I have a pretty good idea. Well, in fact, I'm not going to graph it yet. I'm going to see what's happening with my limit. So, it was all right there. Did you spell something? No. Anyway, what's that? Okay, sure, it's fine. Hopefully it's fine. So I don't know which way is going up. So let's actually look. Let's look at the limit as x approaches 2 from the right. Now, if I plug in 2, I'm going to get 12 on top. I'm going to get 4 minus 4 on the bottom, which is 0. Here's where I want to be a little extra specific. Technically, the number I'm plugging in is a little bit bigger than 2. And if it's a little bit bigger than 2 and I square it, it's still bigger than 2. And sorry, it's still bigger than what? I mean, it is bigger than 2, but 2 squared is really bigger than 4, right? So it's like 2.01 squared is bigger than 4. And then 4 minus a number that's bigger than 4 is going to be very close to 0, but slightly negative. So I have a positive number divided by a negative number, and a positive divided by a negative is going to be negative, and it's going to be a negative large number. That's right. So if, right, you could take out a calculator. I could take out a calculator. Right, if I plug in, say, like 2.01, and I square it, you can't see what I've tried to show people. You can almost no, that's terrible, right? You can't see that. No, let me just do it and tell you. 2.01 squared is 4.0401, and you subtract that from 4, you get negative 0.0401. And if you do 12 divided by that, you get about negative 300. So as you can see, as x gets really close to 2 from the right, the y values get very negative. So we're going down like this. Because the closer x gets to 2, the more negative y gets, at least on the right side of 2. On the other hand, if we look at the limit as x approaches 2 from the left, similar things happen, except now the denominator is very slightly positive because we're putting a number in that's just a little bit less than 2, like 1.99, squaring it, getting something a little bit less than 4. 4 minus a smaller number is slightly positive, so the whole thing is positive. So on the other side of 2, we have positive infinity. We're going up to infinity. Now I've drawn this poorly because if I plugged in 0 for x, I would get 0 over 4, which is 0. So I should actually like hit the origin and do something more like that. Sorry, I wasn't prepared to graph the whole thing. And then let's see what happens near the other vertical asymptote. Let's see what happens as I approach to negative 2 from the right-hand side of 6x over 4 minus x squared. And now we'll be honest here. It's hard for me to think about if I'm on the right side of negative 2, I mean, bigger, but what does that really mean? It's going to be a lot easier if we factor the denominator here. So I would rather write this as the limit as x approaches negative 2 from the right of 6x over 2 minus x times 2 plus x. It's still hard for me to think of what's going on, to be perfectly frank. But let's figure it out. So on top, I'm going to get 6 times negative 2. On the bottom, 2 minus negative 2 is 4. 2 plus negative 2 is 0. And if I'm a little bit bigger than negative 2, then I'm going to end up being a little bit bigger than 0. Because a little bit bigger than negative 2 is like negative 1.9. If I'm the right side of negative 2, I'm slightly... Oh, there's something else, yeah. It reminds me of something else I need to talk about too for just a minute. So I'm going to be slightly positive here. So it's going to be a very slightly positive 0. Which means I have a negative over a positive, which is going to be a negative infinity. So on the right side of negative 2, we're going to be going down to negative infinity. On the other side of negative 2, now I know what's going to happen already. I know that because both of these vertical asymptotes came from factors that have an odd power, you're going to get the opposite behavior on either side of your vertical asymptote. One side has to go down, one side has to go up. On the other hand, if it came from an even power, both sides would go the same way, either both up or both down. Here, we can also look at the limit though. The limit as x approaches negative 2 from the left of 6x over 2 minus x times 2 plus x. everything does the same thing except for the 0 part. So we get negative 12 on top. So we got 4 over there. And then 2 plus a number a little bit smaller than negative 2, like negative 2.1, is going to be a slightly negative number. So you have a negative over a negative, which is going to be a positive infinity. So as we approach negative 2, from the left side, we're going to go up, 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 up to infinity. Could you explain once more why we're taking both of the one-side limits to each number? So really because I decided to. So I wanted you to see that when you, so really I started this by asking, where do we have vertical asymptotes? And we have vertical asymptotes at where the denominator is 0 and the numerator is not. But really, I could have asked this question and said, like, take these limits. And then we take these limits and you get a limit as x approaches a real finite number, like 2 or 3 or negative 5 or whatever. If you end up getting infinity or negative infinity as what the limit is, that means we have a vertical asymptote. As x approaches 2, the function is getting very, very, very negative, or from the left-hand side, very, very, very positive. Same deal for negative 2. As we approach negative 2 from the right, the function gets very negative. As we approach negative 2 from the left, the function gets very positive. So that's why we're doing this. But really, we're doing it because I decided. We might as well, while we're here, talk about the horizontal asymptotes. I've drawn this in a way that's made it, I don't know, it's not clear. I don't know if it's clear or not. So how do we find horizontal asymptotes? Horizontal asymptote is really just asking what happens to this function as you go way, way out to the right or way, way out to the left. And it can either get close to a particular number or it doesn't. But the way we evaluate that is by taking the limit as x goes to infinity. But I like the do it, and I'm trying. Sure, fine. Feel bad squeezing this in over here, but not bad enough to not do it. So, as x goes to infinity, what happens to 6x over 4 minus x? The most methodical way or algorithmic way of doing this, when you have a rational function, is to divide every term by the highest power of x that's in the denominator, not the numerator. So specifically, when the numerator has a higher power, you don't want to divide by the highest, right? Because we'll do it again. Well, so I would say no to your question, Litzy. To find the vertical asymptotes, you don't have to take the limits. To find the vertical asymptotes, you have to identify where this sort of rational function has not 0 divided by 0. But to really show that the vertical asymptotes, like if I was giving you this as a test question, I said graph this thing, find the vertical asymptotes, you would just have to say 4 minus x squared equals 0, it gives you x equals 2, x equals negative 2. You wouldn't need to do all this work about showing one side went up to infinity, one side went down to negative infinity. You could show that work, it might help you graph it, but it's not required. But definition wise, if you look at the book, the textbook does say like we define like x equals a to be a vertical asymptote if the limit as x approaches a from the right goes to either infinity or negative infinity, or the limit as x approaches a from the left goes to infinity. Or basically, if any of the one-sided limits or the two-sided limits go to either infinity or negative infinity, that's a vertical asymptote. So this is kind of the definition of what makes a vertical asymptote. But as far as finding them, it's usually as easy as just setting the denominator equal to 0 and solving for x. The one exception to that would be logarithmic functions. Logarithms are the only other kind of function that really have a vertical asymptote where it's not because you're dividing by 0. Anything else, trig functions included, you get vertical asymptotes when you have division by 0. Logarithmic functions are the only other ones. So when you take the log of 0, right, you can't take the log of 0, but when you take the log of something that's getting closer and closer to 0, the function gets really, really negative typically. So to deal with this, take this limit, I would personally choose to divide every term by x squared. So 6x divided by x squared, 4 divided by x squared minus x squared divided by x squared. In essence, what you're really doing is multiplying the top and bottom by the same thing. You're multiplying the top and bottom by 1 over x squared. And then we're going to simplify. So we're going to get the limit as x goes to infinity. The top is going to be 6 over x. The bottom is going to be 4 over x squared minus 1. Here's something that comes up all the time. As x goes to infinity, or as x gets really, really big, what happens to 6 divided by x? Does that fraction get really big or really small? Small. If the denominator gets big, the fraction gets small. And the bottom, 4 divided by x squared, has the same fate. In the fraction 4 over x squared, the denominator is getting really, really big. So the fraction is getting really, really small. And then -1 is just -1. So 0 over -1, 0 divided by -1 is 0. So what we're saying is as x gets really, really big, the y values get closer and closer and closer and closer to 0. And since I don't want to write all the work again, I will point out that in a rational function, the horizontal asymptote to the right is always the same as the horizontal asymptote to the left. Or if you look at this, it wouldn't matter if this x were going to positive infinity or if it was going to negative infinity. You would still have the same result of 6 divided by negative infinity is still super duper small or super duper close to 0. 4 divided by negative infinity squared is still very, very close to 0. It's just, well, this one's just slightly negative, this one's just slightly positive. So the only difference is it's going to look like, I just said something that was, oh no, that's fine. Yeah. It's going to look like this. I will also point out, just because people often have confusion about this, this graph does cross its horizontal asymptote right at the origin. It's totally okay. Graphs do that all the time. Totally, totally, totally cross the horizontal asymptote. Let's look at a few more examples of horizontal asymptote things because they can be a bit confusing. So the general idea is that for a rational function, to find the horizontal asymptote, you simply divide everything by the highest power in the denominator. So for example, if my function were, say, f of x equal to 2x squared plus 5x minus 1 over 7x squared plus 3. If I wanted to find the horizontal asymptote, if someone says find the horizontal asymptote, what they really mean is take the limit as x goes to infinity and negative infinity. We just think about them separately. So one way of doing this, like I said before, is to divide everything by the highest power of x that's in the denominator, which it would also be x squared in this problem. An equivalent way of doing that, which some people prefer, so I'll show it to you that way, is factoring out the highest power of x in the denominator. Interesting. Never thought of it that way. Or just the highest power in each. We'll think about, we'll cross that bridge when we get there. So I write this as the limit as x goes to infinity of, I'm going to factor out an x squared from the bottom. So watch this for a second. Factoring or dividing out an x squared, I get 7 plus 3 over x squared. You're still really dividing each thing by x squared. You're just writing the x squared out in front. Same deal on top. I'm going to factor out an x squared. I'm left with 2 plus 5 over x minus 1 over x squared. X squared divided by x squared is 1. So then we're left with the limit as x goes to infinity of 2 plus 5 over x minus 1 over x squared over 7 plus 3 over x squared. And just like in the previous problem, x is getting really large. 5 divided by x is getting closer and closer to 0. 1 divided by x squared is getting closer and closer to 0. Anything divided by x or a power of x is getting closer and closer to 0. So this limit ends up being 2/7, which means we have a horizontal asymptote at y equal to 2/7. There is a pattern that emerges when you look at limits of rational functions where the degree on top and the degree on the bottom are the same. So for example, if I said, what's the limit as x goes to infinity of 3x plus 5x squared plus 2x to the 4th over 1 plus 9x cubed plus, I don't know, 6x to the fourth. Which is written in not the nicest way ever, right? That's not how a normal mathy person would write it. They would write the highest powers first in decreasing order. But well, let's do the work. You might, I did something I don't love here. I'm going to change this 1 here to a 10, just because I don't want any ambiguity about what's about to happen. So, we'll take the limit. I personally prefer dividing versus factoring out, but either way is fine. You can do whatever you like. So let's divide everything by x to the what? Right, the highest power in the denominator, x to the fourth. So we're going to write this as the limit as x goes to infinity. I think you can skip the step I'm about to write of actually writing everything divided by x to the fourth. This step is probably a bit tedious. And go straight to the step where you simplified it and write it as the limit of 3 over x cubed plus 5 over x squared plus 2 over 10 over x to the fourth plus 9 over x plus 6. And then, just like before, all the things that are being divided by x to a positive power are going to get closer and closer to 0. So we end up with 2 over 6. 1/3. Typically on your first exam, if your teacher is asking you about limits to infinity like this, they want you to show this work. Typically after your first exam, if you're being asked about limits like this, you can use what we typically refer to as the shortcut, which is that if the degree on the top and the degree on the bottom are the same, the highest power on top, highest power on the bottom are the same, then the limit is going to be that fraction or quotient of leading coefficients. Even if they're not written first, the 2 is the leading coefficient in the numerator. The 6 is the leading coefficient in the denominator. And so the limit is the fraction or quotient of those 2 coefficients, 2 over 6. So we could look at something else like, for example, the limit as x goes to negative infinity, sure, let's change it up, of 5x to the 7th plus 3x to the 4th minus 2x plus 1 over 9x to the 7th plus 8x squared plus 7. And know without a shadow of a doubt, the limit is going to be 5/9, because the degree on top and the degree on the bottom are both 7, which is the same. And so then it's just going to end up being 5/9. You should still show the work at this juncture, because your teacher is going to expect to see it unless they explicitly say they don't want to see it. But after that, we usually just be like, yeah, we all know the thing, so we'll do the thing. On the other hand, if the degrees are not the same, different things happen. So if we looked at something like, say, the limit as x approaches infinity of 4x cubed plus 8x plus 1 over x to the 5th plus 7x squared minus 9. Logically speaking, that's terrible. That's logically. If we think about this for a minute, we can observe that the denominator is going to overpower the numerator. X to the 5th is going to grow faster than x to the 3rd. So eventually, the denominator is going to be much, much larger. And in a fraction where the denominator is large, the whole value is small. I should say, when the denominator is larger, the whole fraction is small. You can even think about plugging in a number, right? If you plug in x equal to like 1,000, 1,000 cubed is 1 billion. 4 billion on top, about. 1,000 to the 5th is a quadrillion, right? This is 1,000,000 times bigger than that. So if the denominator is 1,000,000 times bigger, the whole fraction is going to be small. But the work we would show would still be to divide everything by x to the 5th. Okay, I'm going to skip that first step and just divide everything by x to the 5th. So divide by x to the 5th, and we're going to get 4 over x squared, 8 over x to the 4th, 1 over x to the 5th, and the denominator 1 plus 7 over x cubed minus 9 over x to the 5th. And just like the previous times, everything divided by x to a positive power is going to get closer and closer to 0 as x gets larger and larger. So we end up with 0 plus 0 plus 0 over 1 minus plus 0 minus 0, which is going to be 0 over 1, which is 0. So not surprisingly, when the denominator has a higher degree than the numerator, the limit's going to be 0. And that's always true for rational functions. And then thirdly, what if we had the flip of that? What if we had the limit as x goes to infinity of x to the 5th plus 7x squared minus 9 over 4x cubed plus 8x plus 1? Well, I think we can expect that now the numerator is going to get really big compared to the denominator, and the overall value of this is going to be large. I should point out, by the way, in this previous two problems, here we'd have a horizontal asymptote of y equal to 5/9. Here we'd have a horizontal asymptote of y equal to 0. This especially is where you have to adhere to dividing by the highest power in the denominator, because this is the one case where the highest power is not in the denominator. If you were to divide everything by x to the 5th, it would be challenging to figure out what was happening here. If we divide everything by x to the 3rd, on the other hand, things will work out fine. So dividing everything by x to the 3rd, I'm going to get x squared plus 7 over x minus 9 over x cubed over 4 plus 8 over x squared plus 1 over x cubed. I divided everything by x cubed. Now, as everything goes to infinity, as x goes to infinity, all these things divided by x to a power go to 0. But notably, we're still left with an x squared here. So what we really get here, and this is kind of weird to write them right anyway, we get infinity squared plus 0 minus 0 over 4 plus 0 plus 0. And infinity squared is still infinity. And infinity divided by 4 is still infinity. So this is infinity. Meaning, if you were to graph this and you went way, way, way to the right, the y values would get larger and larger and larger and larger forever and ever and ever. It would also mean that there's no horizontal asymptote, because the function's not getting close to any particular y value. It's just getting larger and larger and larger. What do you think is going to happen if we go to negative infinity? We go way to the left, are the y values going to get really, really large, or really, really negatively large, or neither? It depends on the difference in degrees, actually. So here, I mean, really what you do is you do the same work. So if you do the same work, limit as x goes to negative infinity. Let's just start right over here, since we already know we're going to divide everything by x cubed. It's going to be x squared plus 7 over x minus 9 over x cubed over 4 plus 8 over x squared plus 1 over x cubed. And you're going to get negative infinity squared plus 0 minus 0 over 4 plus 0 plus 0. And that's still going to be positive infinity over 4, which is positive infinity. So I know, in fact, I don't know, but I can find out. I don't know exactly what this graph looks like, but I know that it looks something like this. This graph does something like it goes way up that way. Some weird stuff happens in the middle, and it goes up like that. It's a very not good picture of what this graph does. We could actually take a look, though, for 1 second. We might as well use the tools we have available to us. I would encourage you all to, become well-versed in using Desmos. Or Desmos 3D when you get to 21C. There's some cool stuff there too. But if we graph, I'm always in the way. If we actually graph this thing, which is kind of hideous, y equal to, on top, we've got what here? X to the 5th. Can I do it? Maybe. Maybe not. X to the 5th plus 7x squared. It's going to be gross, but it'll be good. Minus 9 divided by 4x cubed plus 8x plus 1. Let me zoom out. Yeah, right? Weird stuff happens in the middle. There's a vertical asymptote. But then at the end, it actually looks parabolic. And that's not a coincidence, because if you actually divide x to the fifth by x cubed, you get x squared. In fact, I can show you this graph has a parabolic asymptote. If we graph y equal to, I think it's x squared divided by 4. I didn't actually check, so I don't know. Yeah, look at that. If I zoom in a bit, this graph, right, in the middle is not super close to y equals x squared over 4. But as you move away from the middle, that graph is super duper close to x squared over 4. It is literally a parabolic asymptote. Kind of neat. So, with rational functions, one of three things can happen. If the degree on the top and the degree on the bottom are the same, the limit is the quotient of the leading coefficients. If the degree on top is smaller, the limit's 0. And if the degree on top is larger, the limit's some sort of infinity. It might be positive. It could be negative, though. So just to kind of make sure that everyone, let's do one more example just so we can see that. If I was looking at something like y equal to, what have I got here? Sure. Sorry, 4x plus x cubed over 2 minus x squared. Looks kind of funky. But if I took the limit as x goes to infinity of 4x plus x cubed over 2 minus x squared. I'm going to do it the other way. I'm going to factor out this time just to change it up. But again, if you, whichever way you like to do it that way. And what am I factoring out from the top and the bottom? X to what power? So I'm going to write this as the limit as x goes to infinity of x squared times 4 over x plus x on the top, and x squared times 2 over x squared minus 1 on the bottom. And then I cancel or divide those things and get 1. So that's going to be the limit as x goes to infinity of 4 over x plus x over 2 over x squared minus 1. And that's going to end up being 0 plus infinity over 0 minus 1, which is infinity divided by negative 1, which is negative infinity. So as we go to the right, this graph goes down, 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 down. And then on the other side of things, if we look at, in fact, I don't really want to do the work. And there's really, all I have to do is go back to the place where things that would change. So right here, all the work would be the same. So this limit as x goes to negative infinity would be the limit as x goes to negative infinity of 4 over x plus x over 2 over x squared minus 1. I'm still going to get a 0 plus, but now it's going to be plus a negative infinity over still a 0 minus 1. And that's a negative over a negative, so that's going to end up being positive infinity. So to the right, this graph gets really, really negative. To the left, this graph gets really, really positive. Okay. We should do one more. One more limit to infinity that's kind of funky. And then we'll talk about some tangent lines. So here's one that you might have seen, something like the limit as x goes to, let's make it exciting. Limit as x goes to negative infinity of x plus the square root of x squared plus 16x. Kind of funky. I will point out that if you were to plug in negative infinity, you would get negative infinity plus the square root of, let's actually, I'm going to make this a little bit easier for us to see. I'll point out that x squared plus 16x is the same as x times x plus 16. If I plug in a negative infinity there, that's going to be a negative infinity times a negative infinity plus 16. Okay. Negative infinity plus 16 is still negative infinity. Times negative infinity is positive infinity. And what's the square root of positive infinity? It's still infinity. Infinity, infinity. Right? The square, or I should really say, when you hear infinity, or when I say infinity, what you should really hear is a really big number. So a negative really big number times a negative really big number is a positive really big number. And the square root of a positive really big number is a positive really big number. So a really big positive number plus a really big negative number. Who knows? Could be anything. This is what's called it's actually not called this. It's not called a negative infinity plus infinity. It's more accurately called an infinity minus infinity form. This is an indeterminate form. Just like 0 divided by 0 can end up being anything when we do a limit, or infinity divided by infinity can end up being anything when we do a limit. Like the previous limits we just did, where the top was getting big and the bottom was getting big, and the answer could be 0, or infinity, or negative infinity, or 5/9, or 2/7, or literally anything. This is another example of an indeterminate form. And when the form is indeterminate, what that really means, you know what that really means? It means you got to do more work. That's literally, really, I mean, when you see an indeterminate form, whether it's 0 divided by 0, or infinity divided by infinity, or infinity minus infinity, you have to do something. Factor and cancel, multiply by a conjugate, get a common denominator, divide everything by the highest power of x. It just depends on what we need to do. Here, actually multiplying by the conjugate is going to be real helpful. So we're going to rewrite this as limit as x goes to negative infinity of x plus the square root of x squared plus 16x divided by 1, multiplied by the conjugate of that over the same thing. So x minus the square root of x squared plus 16x divided by the same thing. Okay, so multiplying out the conjugates like we do, right? That's the whole point of multiplying with the conjugate, is the conjugates multiply and you get something kind of nicer. We have the limit as x goes to negative infinity of, well, the bottom's just going to be x minus the square root of x squared plus 16x. The top is going to be x times x, which is x squared. The middle terms cancel. That's why we multiply by the conjugate. And finally, positive something times negative something is going to be minus the square root of x squared plus 16 squared, which will just be x squared plus 16x. I didn't say the x when I said it before, but it was there. Simplifying the numerator, the x squareds end up subtracting to 0, and you have the limit as x goes to minus infinity of negative 16x over. Okay, before I write the bottom, well, I'm going to do something a little bit different. So I want you to observe. The highest power in the numerator is 1, x to the first. And even though the denominator isn't a polynomial, right, it doesn't have a degree technically, the highest power in the denominator is kind of also 1. Because you have an x to the first here, and even though you have an x squared there, it's a square root of x squared, which is, again, not exactly like, but close enough like to having a highest power of 1. So what we're going to do is we're going to try and factor out an x to the first in the top and the bottom. But to be able to do that, we have to get it out of the square root first. So what I'm going to do on the bottom here is I'm going to write this as x minus, and then inside the square root, I'm going to factor out an x squared. We have x squared times 1 plus 16 over x. I'm going to rewrite this because there is something really important to see here. So you have the negative 16x on top. You have an x minus. When you have the square root of a product of things, like the square root of 4 times 9, you can either think of it as the square root of 36, which is 6, or you can think of it as the square root of 4 times the square root of 9, which is 2 times 3, which is 6. Meaning, when you have the square root of this times this, you can break it up. You can write that as the square root of x squared times the square root of 1 plus 16 over x. Totally valid. All right, and here comes the trick question. What's the square root of x squared? I said it was a trick. It's not just x. It's the absolute value of x. And here that's actually really important because the square root of x squared is just x if x is already positive. But, or the absolute value of x, right? The absolute value of x is just x if x is already positive. But if x is negative, which it certainly is, because x is going to negative, it's as negative as it ever could be, then the absolute value of x is actually equal to negative x. So that when you plug in the negative value, you then take the negative of it and it becomes positive. It's kind of weird. Let me graph it just so you all, just to remind you all. You all know what the absolute value function looks like. What letter of the alphabet does it look like? Looks like a really wide V. I think you all believe this, right? You all believe that this is the graph. Well, if you believe this is the graph, then you know what I'm saying. You just don't know that you know it, right? Over here, to the right of the origin, that's where x is greater than 0. And the graph is the graph y equal to x. So if x is positive, then you need y to equal x. On the other hand, on the other side, over here, if x is less than 0, what's this piece of the graph? What line is that? Y equal to, doesn't have a positive slope, it has a negative slope. Y equal to negative x. So it's literally the case that the absolute value of x is equal to positive x when x is already positive, and negative x when x is already negative. So that the negative of that negative becomes positive. And then you can include the 0 in whichever piece you decide you want to include. It doesn't matter if you put the equals here or here. So what that means for us over here is that when I rewrite this, check this out. This square root of x squared is equal to the absolute value of x. And in this case, that is going to be negative x. So we're going to write this as the limit as x goes to negative infinity of negative 16x divided by x minus negative x times the square root of 1 plus 16 over x. Kind of gross. But we're almost done. So I'm going to do one thing here. I'm going to rewrite this so it doesn't look quite so ugly. It's going to be negative 16x on top. It's going to be x plus x times the square root of 1 plus 16 over x on the bottom. And now I'm going to factor out an x to the first from the top and the bottom. So I'm going to write this as the limit as x goes to negative infinity of x times negative 16 on top over x times 1 plus 1 times the square root of 1 plus 16 over x on the bottom. The x divided by x is 1. And then when I take the limit of the rest, you have the limit as x goes to minus infinity of negative 16 over 1 plus the square root of 1 plus 16 over x. As x goes to negative infinity, 16 over x gets really, really small. Also, I just want to point out, this would be super problematic if it was a minus sign there instead. If that was a minus that, we'd have 1 minus 1 in the denominator, which would be division by 0, which would be weird. So we end up getting negative 16 over 1 plus 1, which is negative 8. Kind of a strange limit. Kind of a question teachers like to ask. All right, what's that? All right. I know what's nothing. All right, sorry. All right, so limits are never going away. So like right at the end of the quarter, we'll come back to talk about limits some more because we talk about L'Hopital's rule. And 21B, limits will be a thing. And 21C, use limits to evaluate whether a series is convergent or divergent. I don't remember if they show up in 21D, but I can't imagine they don't. Limits are not going away. Get comfortable with them because they're going to stick around for the rest of your mathematical career. I'll say it again. All of calculus is kind of based on, at some level, how limits work. because all of calculus is kind of based on derivatives, and derivatives are defined in terms of limits. So don't sleep on limits. They're not going away. Make sure that you practice them as much as you can to feel comfortable with them. Let's start moving towards talking about the definition of the derivative. Although it's a path. So we'll start with some average rates of change. So yeah. So average rate of change. Oh, and yeah, sorry, there was one other thing I promised I would say something about. Let me briefly just, so I'm going to go to another page for 1 second because there's one other function I forgot to mention that someone was asking me about at the end of last class. It's like, oh, by the way, if you think, like, if you're going to ask me something at the end of the class, ask me during class. Not that I'm not happy to give you my time, but like this person asked this question. It's like, oh, that would have been a great question for everyone to have seen. Because now I'm going to take some time right now to talk about it. But there's a function that you might have seen that looks like this. Or someone might have written it as this with 2 vertical lines. It's annoying to write. And it's got like 3 different names. It's either called the floor function, maybe only 2 different names, or the terrible name, the greatest integer less than or equal to x function. Greatest integer less than or equal to x function. Also, it's called a step function, although there's 2 different step functions that you should be aware of. So what this function is, it's literally what we just said. It is the greatest integer less than or equal to x. So for example, if I said, what's f of 3? The biggest integer less than or equal to 3 is 3. If I said f of 3.2, I'd still get 3. If I said f of 3.5, I'd still get 3. If I said f of 3.9999728, which is really, really close to 4, I'd still get 3. It's not a rounding function. It's a function that gives you the biggest integer that is less than or equal to the input. For positive numbers, it feels like you're just cutting off the decimal. It's not true for negative numbers. For negative numbers, if I plug in, say, -2, the biggest integer less than or equal to an integer is that integer. But if I did say f of, say, -2.3, the biggest integer less than or equal to -2 is -3. Right? Because you have to be more negative than -2.3. It makes it maybe a little bit easier if you look at the number line. Right? If you pick a number between -2 and 3, and you say, what's the biggest integer that is less than that or left of that, it's got to be -3. So I really just wanted you to see this function because it pops up occasionally. It's another example of a piecewise function that's not written as a piecewise function because we come across it often enough. Here's how to graph it. I wonder, I'd be willing to bet it's in Desmos somewhere. Like if you Googled how do I graph the floor function in Desmos, there'd probably be a way of doing it. But it's not too hard to graph. The reason it's called a step function is because it looks like a staircase. Yeah, exactly. So if I plug in 0, I get 0. And if I plug in any number between 0 and 1, I still get 0. So I plug in 0.1, 0.2, 0.5, all the way up to 1. Like I plug in 0.999, I still get 0. Then when I plug in 1, I jump up to 1. And then any number bigger than 1, but still less than 2, will give me an output of 1. So I get all those values there. So basically, you keep jumping up. At 2, I jump up to 2. I'm going to draw an open circle at the same level over at 3 and then connect them like that. And then at 3, I jump up to 3. And you just keep going like this forever and ever. Same to the left. Between x equal to -1 and x equal to 0, the biggest integer less than or equal to numbers between -1 and 0 is -1. So the y value is -1, and so on and so on. So this is the floor function. There is also a ceiling function, which does kind of the reverse. It gives you the smallest integer greater than or equal to your input. So, and it looks kind of like this, but just shifted a little bit. So the ceiling function, which is something like this, where you put the little bars on top instead of x, is the smallest integer bigger than or equal to x. So for example, the ceiling of 4.2 would be 5. The ceiling of -2.1 would be -2, and so on and so on. If you have a moment, I would encourage you to try graphing the ceiling function on your own. I think it's this function like shifted one up, but then like the open and closed points are on the opposite sides. Like the closed points on the right and the opposite points on the left. I think that's how it looks, but I'm not 100% sure because I haven't thought about it in a while. Okay, that's all I wanted to say about that. I just wanted to make you aware of this function because it does come up and sometimes people don't do a great job of explaining it. So average rate of change. So let's say we're looking at the function f of x equal to x squared plus 6x. And we want to look at the interval from 1 to 3. By the way, well, not fine. Let's graph this poorly. When I say poorly, I mean I'm going to graph the function not very well to scale. So x squared plus 6x is an upward opening parabola. It would have an intercept at the origin and at -6. I'm just going to draw. You here for Co-21A? No, that's not. That's. I don't know if that means who's it with. Dr. Deneau. Oh, for the actual class. Yeah, that meets after this, or maybe in another room. I don't know. So I'm sure that's the discussion. Anyway, so here's vaguely what the graph looks like. Some parabolic thing. And I'm looking to find the average rate of change between x equal to 1 and x equal to 3. And again, this graph is not super to scale. I'm just trying to draw it reasonably well. So to find the average rate of change, you're looking at the difference in the y values over the difference in the outputs versus the difference in the inputs, or divided by, I should say. So my average rate of change here is going to equal f of 3 minus f of 1 divided by 3 minus 1. Graphically, right, it's this difference here. So there's f of 3. There's f of 1. And there's my delta y. And then down here, here's my delta x. Another way to view this is that we're finding the slope of the line that connects these 2 points, which is called the secant line, or a secant line, I guess, because right, there's many secant lines. So we're finding the slope of that line. The slope of that line in this case is going to be, well, let's see, f of 3 is going to be 9 plus 18 minus f of 1 is going to be 1 plus 6 divided by 3 minus 1. That's going to be 27 minus 7 over 2, which is going to be 10. So the slope of that line, that average rate of change is going to be 10. Meaning that from here to here, if you increase x by 1, you correspondingly increase y by 10. Okay. What if we shorten the interval? So instead of looking at the average rate of change on the interval from 1 to 3, what if we did the same thing? Let's call this a, I guess. But now we want to find the average rate of change for the same function on the interval from 1 to 2. Well, let me ask everybody, just looking at the graph I've done, that's I know not perfect, but still has the right direction. if instead of using these 2 points, I do want everyone to look real quick. Instead of using these 2 points, if I use this point and now this point, would we expect the slope to be a higher positive number or a smaller positive number? Is it steeper or less steep? It's less steep. So we'd expect the slope to be a smaller positive number. And it's good to look at the graph and be like, what do I think is going to happen before I actually calculate the things down? I'm just going to draw it here. So let's say here's 2. So now I'm finding the slope of this secant line. So now the slope of my new secant line is going to be f of 2 minus f of 1 over 2 minus 1. Plugging in 2, I get 4 plus 12. Minus plugging in 1, I still get 7. Or 1 plus 6, if you like. Divided by 1. That's going to be 16 minus 7, which is 9 over 1, which is 9. So yeah, the slope is less. Not a lot less, but less. And if we keep doing this, so let's do one more. If we want to find the average rate of change, maybe on, say, on the interval from 1 to 1.5, same idea. We're going to find f of 3 halves, or 1.5, minus f of 1, all over 3 halves minus 1. That ends up being, so I'll just tell you instead of walking you through the calculation. F of 3 halves ends up being 45 fourths. F of 1 is still 7. 3 halves minus 1 is 1 half. 7 is 28 fourths. 45 minus 28 is 27 fourths. And dividing by 1 half is the same as multiplying by 2. Oops, did I make a mistake? I did make a mistake. 45 minus 28 is not 27. 45 minus 28 is 17. Sorry about that. It's good to be careful. And then we're multiplying by 2 over 1. That ends up being 17 over 2, which is 8.5. If you kept doing this, you'd be getting closer and closer and closer to the value of the tangent line. So if we let this point here get closer, oh, sorry, you can't quite see that, apologies. If we let the point right here is, 1.5, and here's our, and it's hard to see because the graph gets kind of messy. But as the points get closer and closer to each other, the slope of the secant line gets closer and closer and closer to the slope whatever the tangent line would be because those points are so close. Yeah. 17 times 2 is 32. Yes, but it's 17 divided by 2. Oh. Right. So it's 17 over 4 times 2 over 1, and the 2 and the 4 cancel and leave me with a 2 in the bottom. Yeah, but good question. So what we're trying to do is we're trying to actually find the slope of the tangent line by doing the following. We want to take the limit to find the slope of the tangent line here. We're going to find the limit as x approaches 1 of f of x minus f of 1 over x minus 1. Right, instead of doing between 1 and 3 or 1 and 2 or 1 and 1.5, what we're now doing, and I will draw this picture again because I think it's worth drawing. Here's 1, f of 1, and here's x, and here's f of x. And the idea is that we're letting x move towards 1 so that the slope of this secant line gets closer and closer and closer to being the slope of the tangent line. This is why we have spent so much time practicing limits of the 0 over 0 type. Because if you just plugged in 1 for x, you'd have f of 1 minus f of 1, which is 0, over 1 minus 1, which is 0. So this is a 0 over 0 type of limit, which we know how to deal with. So let's do it. So reminding you all that the function that we're looking at is f of x equal to x squared plus 6x. We're going to find the limit as x approaches 1 of x squared plus 6x minus f of 1 for the 4th time is still 7 over x minus 1. And now if we plug in 1, we know what's going to happen. We're going to get 0 over 0. So we don't do that. We try to do the usual thing. If you have a 0 over 0 limit, what can I try to do? That would be an option if there was a square root. I mean, I should say, it's always an option. It's not the option I want here. Just factor and cancel. So we know since we plugged in 1 and got 0, x minus 1 should be a factor. X minus 1's a factor, and the other factor has to be x plus what? Gotta be 7. And because the -1 times the 7 has to equal the. So whenever I'm looking for the factors, I'm always focused on the first thing and the last thing. The x times x has to give you x squared, and the constant times the constant has to give you the constant. So here, the -1 times the 7 has to give you the 7, the -7. And then if you want to check, the -1x plus the 7x will give you the 6x in the middle. But I never look at the middle term when I'm trying to factor it until if I've already got one factor. Those divide out to 1. You're left with the limit as x approaches 1 of x plus 7, which is 1 plus 7, which is 8. So the slope of the tangent line here is actually m equal to 8. So f of x equal to x squared plus 6x has a tangent line at the point 1, 7 with a slope of 8. With all this information, we might as well find the equation of the tangent line. If you know the slope and you know the point, you can always write the equation. If it were me, I would start by writing the equation of the tangent line using the point slope form. Y minus the y coordinate equal to the slope times x minus the x coordinate. And sometimes that's a perfectly good way to leave your answer. Most of the time, people want you to write it in the y equals mx plus b form because they're boring. Yeah. Or is that how you want it? Is that how you want it? Or do you have a question? No. Okay. It's okay to be, I'm boring too. Like, it's fine. Like, most of the time we do write it that way. It just always feels like, oh, really? Always this way? Sure, fine. If we add 7 over here, we get y equal to 8x. -8 plus 7 is -1. And there is good reason to write it this way. Reason 1, it shows you where the y-intercept is. Reason 2, it's unique. Meaning if you always write the equation in the slope-intercept form, every different line will have a specific unique equation. Whereas there's lots of different ways I could write it in the point slope form. I could pick 1,000 different points and write it 1,000 different ways. So bigger picture, if I want to find the slope of the tangent line to a graph at any point, this is how I would do it. So, yeah. Find the slope of the line tangent to a graph at the point x comma f of x. We can do the following. Now, there are two kind of standard ways of doing this. Oh, sorry, thank you. Yes, please, always. One of them is typically more computationally challenging than the other, and we usually don't do it that way. I will mention it in passing, but I'll tell you the way I think you should do this, and hopefully it's the way your professor is showing it to you. So let's say we have some similar-ish looking graph. Maybe it's a little bit different, like that. And I want to find maybe the equation of the line tangent, or at least the slope of the line tangent right there. I would love to find the slope of that tangent line. Let's use a ruler, James. Yeah. So I would love to be able to find the slope of that tangent line at the point x comma f of x. So what we're going to do, just like we were doing before, is we're going to instead take the limit of the slopes of secant lines. So we're going to throw some other point on here, and I would like a finer point pen here. 1 second. I know I've got one somewhere. There we go. So over here, we're going to say, I'm going to call this the point x plus h, comma, f of x plus h. And so this secant line, draw in green, we know how to find the slope of that secant line. It's the difference in the y's, f of x plus h minus f of x, divided by the difference in the x's, x plus h minus x. And that is the slope of the secant line. I'll also point out that the denominator does simplify right away as to just h. Sorry, really, I can rewrite this as m equal to f of x plus h minus f of x all over h. Notably, not surprisingly, if I took the limit as, well, actually, no, I'm going to say that, yes. So now, if I want to find the slope of the tangent line, I have to let this point get closer and closer to that point, so that I move closer and closer, finding tangent lines. I don't really want to draw because it'll ruin my picture, but I could find tangent lines that are closer and closer to having the slope of the secant line. You can kind of see that, right? See how as these points get closer, the slopes of these lines gets closer and closer to the slope of the red line. So for this x plus h to get closer and closer to x, well, first of all, what's the distance or difference between x plus h and x? The question, what's the answer? Right. So if I want that point to get close to that point, this distance between them has to get smaller and smaller and smaller. And otherwise, we're going to take the limit as h goes to 0 of the slope of the secant line. So the slope of the tangent line is equal to the limit as h goes to 0 of the slope of the secant line. And that's how we define the derivative. So, definition for a function f of x, the derivative written as f prime of x or df dx is the limit as h goes to 0 of f of x plus h minus f of x over h. And something you definitely, sorry, I'm way zoomed in here. I forgot I was so zoomed in. Oh, that's definitely something you want to commit to memory. Specifically, that f prime of x, or the derivative df dx, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, we didn't do the previous problem that way. We found the derivative at a particular point. It was x equal to 1. But we can do this by finding the derivative at any value x. Let me show you what I mean. So I will point out that previously we did this, and I know we're short on time here, but I do want to get you to this one example. So previously, we found the derivative at 1, I should say for f of x equal to x squared plus 6x. We found f prime of 1 by doing the limit as, I think we did as x approaches 1 of f of x minus f of 1 all over x minus 1. Now we're going to do the following. We're going to find the derivative for any value of x. And it's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. These are similar, but they feel kind of different. They're actually really the same. Kind of. Let's see how it works out. So I'm going to plug in x plus h to my function. It's going to be a little bit of algebra. So this is going to be the limit as h goes to 0 of, well, f of x is x squared plus 6x. F of x plus h is x plus h squared plus 6 times x plus h. That is your f of x plus h minus f of x. Be careful here. Notice the mistake I'm making right there. The mistake I'm making is I forgot a parentheses. That minus sign has to distribute to both those terms. Otherwise, things are not going to work out. And then, of course, all divided by h. Here's what should happen every time when we do these kinds of problems. We should expand the numerator, and we should always be able to cancel out every term that doesn't have an h in the numerator. And we might have to do something, we might have to do some other work before we get there. I have to multiply by a conjugate, might have to get a common denominator, bless you. But eventually, be able to cancel out anything in the numerator that does not have an h. And the reason we want that to happen, well, let's see here. If I multiply this out, x plus h squared is x squared plus 2xh plus h squared. Distribute the 6, you get 6x plus 6h. Distribute the minus sign, you get minus x squared minus 6x, all divided by h. It's hard to see that that's a 6x, sorry about that. And I'll point out that x squared minus x squared is 0. And notice here, it's really important that the minus sign distributed because 6x minus 6x is 0. If we'd forgotten that minus sign, we would have had a 6x plus 6x, and they wouldn't have subtracted to 0. Now observe, everything left in the numerator has what? Has an h. I got 2xh, I got h squared, I got 6h. Yeah, there might be some x's left as well. That happens sometimes. But since everything has an h in the numerator, we can factor out an h from the numerator. Because our ultimate goal, whenever we have a problem like this, with this limit definition of the derivative, our ultimate goal is to make that h in the denominator cancel out. And the only way we can make that happen is by factoring out an h from the numerator and dividing it. And then when we can make that happen is for everything that didn't have an h in the numerator to get canceled out in the first place. So those are the things that we need to happen for this to always work. Everything in the numerator that doesn't have an h needs to go away. Everything on the left does have an h. We factor out an h. H divided by h is 1. And then finally, we get the limit as h goes to 0 of 2x plus h plus 6. The remaining h's go to 0, and you get 2x plus 0 plus 6, or just 2x plus 6. And that is f prime of x. And then I'll point out that if you plug in 1, f prime of 1 is 2 times 1 plus 6, which is 8. Just like we saw f prime of 1 was when we did it the other way previously. All right, we have lots more to say about this on Thursday.